We want the support reactions at the wall at A and the roller at C. And we can treat B as a pin. So just looking at the picture, what type of problem is this going to be in order to solve it? Right, it's a frames and machines type problem. We'll have 3 reactions at the wall at A, a force in the Y, a force in the X, and a couple. And then we'll have a 4th reaction at C, just a force in that Y direction. So it's statically indeterminate externally. So it's a frames and machines problem, and in addition to that, we see a distributed load acting on it that we're going to have to account for when we're solving this problem. So we know if it's a frames and machines, we'll need at least 2 free body diagrams to solve it. As I've been doing, I'm going to start with, I'm not going to draw the external picture, although we could. I'm going to jump right to that internal picture. So 3 at A, we have a pin, internal pin support at B that I'll call BY up and BX in this. And we know that from A to B is 3 feet. I have my external supports, my internal supports. I have to account for that distributed load that's acting on just section that goes from A to B. So if we look at the picture, that section of the distributed load, I'll draw it kind of faintly here. We're only looking at the part of the load that touches A to B. We don't care about anything from B to C for this picture. It's a distributed load, and across the entire height of it, the intensity is 500 pounds per foot. When we break it down into the sub-pictures, we have to look at only the load that's acting on that sub-picture when we simplify it. So that's the right idea, but we have to be careful when we're looking at the individual members. So for this, it has a uniform load of 500 pounds per foot, but AB is only 3 feet long. So what we can do is we can find the equivalent load that's acting on AB is the intensity times the length, or we can think of it as a height times a base. So 500 pounds per foot times 3 feet, or 500 pounds per foot times 3 feet will give us 1,500 pounds. That's the load, just the load that acts from A to B. And for this segment of it, it's a rectangle, so it's going to act at half of its base. So in this picture, we have to draw it at the midpoint of the 3 feet. And this is important for finding our supports. And also when we get to the internal drawings, when we draw a segment or a cut segment, that segment only sees the distributed load that directly touches it. So in this case, it was 3 feet of that distributed load. Again, if that was sand and we separate it out, we're replacing that with equivalent point load at the centroid with the 1,500 pounds of force. So this is the simplified picture for just segment AB. We have 5 unknowns here, so I'm going to move on to my second picture before I attempt to write any equations. My second picture, I'll go from B to C. That internal support at B, the directions are already decided for me. My support at C, I just have that vertical piece. And from B to C is a total of 6 feet. For the distributed load, just the part that touches B to C do I have to worry about. For this segment, it is uniform, 500 pounds per foot. From B to C, it acts over 6 feet. So that's going to be 3,000 pounds of the load acts in the middle of BC. As an aside, if I did decide to draw the external picture, which would be okay, then I would see the C, the AY, the AX, the MA, and here this sees the entire distributed load, so I would put at this halfway point the 4.5 feet. that load of 9 times 500, or 4,500 pounds. And this would be an okay picture to draw because I'm including A to B and B to C, so that segment sees the entire distributed load on it. So these three are potential free body diagrams I could draw for this picture. But I'm going to just use 1 and 2 are going to be enough to solve this. But questions on the free body diagrams for this situation. At this point, because I have these simplified free body diagrams, it looks now just like something we saw in the frames and machines because we replaced those distributed loads with point loads. And I'll reiterate, externally, the value we get for C, AX, AY, MA are unaffected whether we simplify it to a point load or try to do it as a distributed load. Internally, though, there is a difference, so these pictures would not be good for if we wanted to know what the force in the actual material itself was. But we'll talk about that at the end of this course. I can start with picture 2 since I only have 3 unknowns attached here. If I take the sum of moments around point C, I'll get 3,000 times 3. And in this picture, plus 6 times By. By, I get negative 1,500 pounds. If I sum forces, I just have negative Bx. So Bx must be 0. And in the y direction, now that I know the value of By, I have a negative By minus 3,000 plus C. So that external force at C, or my reaction at C, 1,500 pounds. And that will be up. Moving on to my first free body diagram. I now know By, I know Bx. I'll have AY minus 1,500 plus By. So my AY value will be positive 3,000 pounds. In the x direction, I have my AX plus BX, but I already know that BX is 0. So AX must also be 0. And finally, if I take the moments around A in picture 1, I'll have the couple, which I called MA and I assumed was positive, minus that 1,500 pounds times 1.5 feet plus 3 times By. So the couple at the wall, to maintain equilibrium, I get a positive 6750 pound-feet. So it is indeed counterclockwise.